Okay, so let's begin by reviewing some basic probability concepts. Probability, of course, is the likelihood of an event or outcome taking place, expressed in p-value 0 to 1 or percent 0 to 100. And I'll note here that we can just denote probabilities in two different ways. We can say P of A, for instance. So the probability of event A happening is 0.5, or equivalently, we could write 50%. We could express as decimals, which we call p-values, or as percents, which I'm sure you're familiar with. Bounded by 0 and 1. 0 means absolutely no chance of this event happening. 1 means it's absolutely certain. Okay, so for example, what's the chance of rain today in East Texas? I haven't looked at the weather report lately, but I'm guessing it's pretty low, 5 or 10%. There's a few clouds in the sky, but we'll see whatever the weather forecaster tells us. Let's just say, for example, it's 5%. Relatively clear winter day here. And we could talk about where he gets that number. It's of course based on historical averages, and then of course the weather conditions today, atmospheric pressure, cloud cover, so on and so forth. And then the meteorologist can feed a lot of things into his model and come up with a number. Chance of Denver Broncos winning the Super Bowl, a little bit different kind of event. We'll talk about the difference here momentarily. Of course, that's given in odds, and it's kind of complicated. I looked online and all I could find was a point spread, and I found a site that converted that. It looked like right now it was 2 to 1 odds against the Broncos. Looks like the Panthers are favored right now. So what does that mean probability-wise? Well, what this means is odds against winning. So this means there's 2 times the Broncos would not win for every 1 time they would win. We've got a total of 3 outcomes, and they win in 1 out of 3 of those outcomes, which would be a P of 0.33 or a 33% probability. We won't work with odds so much in the book or the class, but note that the odds is really technically just a different way of expressing probabilities. Okay, now we want to talk about 2 different types of probabilities, and we've actually just addressed those without categorizing them. They can be objective, which means we can have a lot of historical data about repeatable events that we can use as a basis of estimating probability of the next occurrence. Okay, so what would an example of that be? Well, the chance of rain today in East Texas. And by the way, I looked it up and I was right. It was 5% for this evening. Well, that's based on historical experience for the time of the year and for the current weather conditions, for barometric pressure, humidity, so on and so forth. Okay, so that's objective odds. We have a long history of observations. We have repeated events in a system that we can model with a greater or lesser degree of accuracy. Subjective probability, on the other hand, is assessing unique one-off events, and we can't really estimate that from past observations because there's no consistency or regularity in the system. So an example of that would be the probability, which we just talked about. If the odds were indeed 2 to 1, corresponding to odds against 2 to 1 would correspond to 33% probability of the Broncos winning the Super Bowl. That's subjective. That's based on people who might be experts, kind of evaluating all the unique variables of the situation today. We can't go back and estimate that on all the previous Super Bowls the Broncos have won. Why is that? Well, because the last time they won a Super Bowl, they had an entirely different roster of players. They played a different team, and there's all kinds of variables were different. And in business, of course, we're going to have both of these. We're going to deal with both of these. We're going to have repeated events. You might have a long track record of sales data with a company, or employee turnover data, or something like that. And we could use that as a basis for an objective probability estimate. Or we might have unique events as well, where we have to do subjective estimates of probability.
For the second time in his historic career, Peyton Manning is a Super Bowl champion.
Okay, the next topic to address is the idea of a probability distribution. And this is just a listing of the various probabilities for various proposed events. So as an example here, I've got a probability distribution of a MBA student, let's call him Zane's grade in the research class. Okay, and there's a listing here of 5 possible grades from F to A. And then estimated probability, and this is probably subjective probability based on Zane's own assessment of his chances. Probably only take one MBA research class in your whole life, and so it's not really a repeatable event. But there's maybe an objective component in that Zane could look back on his past experience and performance in undergrad classes and whatnot. So this might be a little bit of a mix, but mostly subjective. And Zane himself assesses that as a 4% chance of getting an F, 15% chance of getting a D, a 36% chance of a C, a 35% chance of a B, and a 10% chance of an A. Now note here, when we add up all of these events, and these events are mutually exclusive, only one of them can happen, and they are exhaustive, which means that they represent all possibilities, they have to add up to 100% or a P equals 1. He's going to get A grade in the class, but assuming that he'll make it through the class, one of these outcomes has to happen. So the sum of the probabilities of each individual event, when they're exclusive and exhaustive, has to add up to 1. Probability rules. I'm going to walk through 4 really important rules that are stated in the book, and we'll review these concepts, work with some quick examples. So there's 4 things we want to know. First off, complement rule. An event or outcome can occur or not occur. Okay, so let's say an event, the probability of A is 0.33. That's the Broncos winning the Super Bowl, let's say. The complement to that event is not A. Probability of not A. Broncos losing. That's going to simply be 1 minus A. So that's going to be 1 minus 0.33, 0.67. The probabilities of exhaustive events have to add up to 1. Well, it's either going to be A or not A. And they don't allow ties in the Super Bowl, so we know the Broncos either win or lose. So the complement rule is very simple, but we'll have to use that in conjunction with some other rules to figure out some of the problems the book's going to throw at us. Okay, next, the addition rule. For mutually exclusive exhaustive events, the probabilities add up to 1. We just kind of covered that with our example, so that's easy. 33% of A plus 67% chance of not A adds up to 100%. Okay, that's easy. Let's keep moving on. Conditional probability. We're talking about the probability of one event given that another event already occurred. Okay, and we'll call these events A and B. And I'm saying, what's the probability of A given, and we draw this vertical bar here, given B has occurred? And that is going to be represented as the probability of A and B. So we want to know what's the probability that A and B together occurred divided by the probability of B alone. Okay, so back to my example, I'm going to define event A as the Broncos winning the Super Bowl. And let's define B, and we know that that probability is 33%. Let's record that. And let's say event B is that the Panthers quarterback, Cam Newton, gets injured sometime in the game. Okay, of course, we know that if Newton goes out with an injury, that would increase the Broncos' chance of winning. And let's say the probability of that by itself is just 2%. Now, if we can estimate the probability that A and B happen together, we can come up with a conditional probability that if B happens for sure, what's the probability of A? So let's estimate that the probability of A and B together, which is Broncos win and Cam Newton gets injured, well, it's probably not going to be equal to the probability that Cam Newton gets injured by itself, because Cam Newton could get injured late in the game. They could be up by several touchdowns, and that still wouldn't help the Broncos. So it's going to be something less than 2%. So let's say it's 1.5%. The chances are if Cam goes out sometime early in the game, that will really help the Broncos. So, but there's a chance that if he gets injured late, the Broncos still might not be able to win. So the probability of the Broncos winning and Cam getting injured is a little bit less than the probability of Newton getting injured by himself. So now I can come up with the probability of the Broncos winning given Cam gets injured. We're just going to put A and B as back over here as 1.5%. Let's do this over here. The probability of A and B, 1.5%, divided by the probability of just B, 2%. And that works out to 75%. So we see that the probability of the Broncos winning would go up quite substantially given the unfortunate event that Cam Newton gets hurt. So that's just an example. We'll use this conditional probability rule again here in a minute when we think about some more business type situations. Okay, and then finally we have the multiplication rule. For independent events, the probability of both occurring is a product of the probability of each event. So we can think about the probability of flipping a coin and getting heads twice in a row. With a fair coin, the probability of heads is exactly 0.5 or 50%, let's say 0.5 this time. Of course, and the probability of tails is 0.5. They're exhaustive, so the probabilities have to add to 1. And the probability of a fair coin is independent of its previous flip. It's a whole new probability each time. So what's the probability of head? Well, that's simply the probability of head, 0.5, times the probability of heads, 0.5. And that equals 0.25. So there's a 1 in 4 chance you'd get 2 heads in a row. And we could keep going. We could say, what's the probability of 3 heads in a row? Well, that's 0.5 times 0.5 times 0.5, 0.125, a 1 in 8 chance, etc., etc. Okay, so if you're familiar with these basic probability rules, you should be in good shape to do the kind of problems that we're going to be doing through the rest of this chapter. Okay, let's do a little bit more practice, and we'll apply these various rules that we've just covered. The probability of rolling a 1 with a 6-sided die is 1/6, or 16.7%. What is the probability of rolling any of the remaining values? So getting anything else other than 1. Well, that of course is going to use the complement rule, which says the probability of A is given. The probability of not A is 1 minus the probability of A. So here our probability of 1 equals 1/6. The probability of not 1, which we could write that the probability of 2, 3, 4, 5, or 6 equals 1 minus 1/6, or 5/6, a 5 out of 6 chance, of course, and there's 5 possibilities, 1, 2, 3, 4, 5, each one's equally likely, 5 out of 6 chance. Okay, so there's just a simple application of the complements rule. Flipping a fair coin, what is the probability of getting 2 heads in a row? We just did that. This is the multiplication or the product rule. 10 heads in a row, probability of 10 heads in a row would be the probability of heads times probability of heads times 10 times, so that'd be 0.5 to the 10th power. 0.00097, very small likelihood. Okay, what's the probability of rolling 2 fair dice and getting a sum of 2? You want to think about what are the ways to get a sum of 2. Well, that's only possible one way. You get 1 on the first die, 1 on the second die. And so we want to think about what's the probability here. 1 out of 6. What's the probability of here? 1 out of 6. Now these are 2 exclusive events, so we can apply the product rule, and we're going to get 1 out of 36, or about 0.028, 2.8%. Okay, so here's a problem I came across when I was preparing the quiz, and you'll be happy to know I did not put this on the quiz, but I found it very fascinating, and it's a neat use of both the conditional probability rule and the rule of complements. So it says, suppose that patrons of a restaurant were asked whether they preferred beer or whether they preferred wine. 60% said they preferred beer, 70% of the patrons were male, 80% of the males preferred beer. Suppose a randomly selected patron is a female. What is the probability that patron prefers beer? So, all right, what we know here, first off from the rule of complements, is those who prefer beer are 60%. And because preferring beer and wine are mutually exclusive, that means preferring wine is 1 minus 60, or 40%. Okay, we're going to write down everything we know. We know that 70% of the patrons are male, so probability of male is 70%. Again, from the rule of complements, 1 minus 70, the mutually exclusive event of being female has to be 30%. Okay. Now, we also know the conditional probability says 80% of the males preferred beer. Well, that's the same as saying given that a person is a male, it's a probability that he prefers beer. So the probability of beer given male. So we're given that they're males, 80% of them prefer beer. Well, okay, what I need is to say the same thing for females. Probability of beer preferred given female. And that's what I'm looking for. Now, I know by the conditional probability formula that I'm going to need the probability of beer and female divided by the probability of female. Now I know this, the probability of female here is 30%, but what I don't know is this, the probability of beer and female. So I got to figure out the probability of beer and female, and I'm going to have to back that out using the conditional probability formula based on what I know about beer and male. And let me show you how I can figure this out. I know that the probability of beer and female, the probability of beer and male, those are exhaustive for the beer lovers, which are 60% of my entire population. Again, I don't really care about the wine lovers right now. I'm just interested in the probability that a given female is a beer lover. If I can figure out one of these, I can figure out the other, because I know that they together have to add up to the 60% of the population of the sample here that are beer lovers. So what I'm going to do is write the formula for population, the probability of beer given male. Well, that's the probability of beer and male divided by the probability male. Okay, and I know that this probability of beer given male is 80%. I don't know probability of beer and male, but I do know probability of male. This is 70%. Aha, so now I can solve for probability of beer and male, and if I solve for that, then I can subtract from 60 and solve for beer and female. So all I have to do is multiply each side by 70%. Okay, 70% times 80%, and that's the same as 0.7 times 0.8, which is 0.56, or 56% is the probability of beer and male. Well, I know that that plus beer and female, because remember, these are all beer lovers here, so that has to be 4%. Now I plug that in up here. Okay, so what I have here is 0.04 divided by 0.3, and that equals 0.133, or to translate back into percent terms, 13.3%. Now, I'm not going to ask you a question this hard. I'm not going to ask you this kind of question on a quiz or an Excel homework for that matter. I just wanted to work through this to demonstrate you the usefulness using the probability rules in conjunction with each other. We can take just a little bit of knowledge and use the logic of the rules to figure a lot of things out. Okay, and finally, let's look at the addition rule. And here's my probability distribution of Zane's MBA research class grade again. And remember, these have to add up to 100 because they are exhaustive and exclusive events. But we can do more with this. We can use the additive rule to say what's the probability of some range of outcomes. Okay, so what's the probability of getting a C or better? Well, 36% chance of getting a C plus 35% chance of a B plus 10% of an A, 81. Okay, so he's got a very good chance of doing decent or well. Likewise, we could say what's the chance of getting a D or worse. Okay, that's all that's all of these probabilities together, because it's going to be this or this. So 15 plus 4, 19%. What's Zane's expected grade? I'm going to jump into Excel just to make this calculation easier. But what I'm going to do is a weighted sum. And this is perfectly legitimate to do with probabilities. So let's put the probabilities in here as the weights. It's a 10% of getting a A, 35% chance of a B, 36% chance of a C, 15% chance of a D, and 4% chance of an F. And by the way, let's add these up some to make sure they equal to 1, which they should. Check, they're exhaustive, right? Do some formatting here. And I now want to say, well, I can't multiply probabilities times letters, so I have to convert these to numbers. And an easy enough way to do it will just be use a midpoint of that range of grades. So that's 95. This is 85. This is 75, 65, and this is anywhere from 0 to 60, so the midpoint of that is 30. And now to take the weighted value, that's just the product. So that equals the weight times the converted value. I'm going to do the same by filling And I'm going to, again, sum those. I'm just going to do that by dragging that formula over. So I could say 77.2, and if I want, I can express that as a percent, is my expected grade based on the probabilities I've established for each of the individual outcomes. Okay, so that's probability basics. Brushed up a little bit. Now we're ready to tackle homework 2.